Alright guys, I am back with the second circuit for our series, Parallel. Again, I just wanted to stop the video in between because my video was already getting up to about 45 minutes and I wanted to end it and not go over, especially over an hour on the one circuit. So with that being said, here is our second example. It's pretty much going to be the same structure as before with what we're trying to find, what we're solving for. Everything's even in the same configuration. We have the resistor first, the capacitor second, and again, it doesn't really matter what order those are. We're going to see the same process going through these guys. So we'll start out. We have our 20 volt peak signal. We have 186 hertz. We have R1 is 4.3 kilo ohms. We have C1 is 330 nanofarads. We have R2 is coming in at 5.6 kilo ohms, and C2 is 1.5 microfarads. R3 is 1.2 kilo ohms, and C3 is 68 nanofarads. Now, again, what we're going to be looking for, the first things we're going to find is we find our capacitive reactances for 1, capacitive reactance for capacitor 2, and for number 3. There we go, that's a good reuse for those. All right, and then after that, we are going to find the impedance from A to B. We're going to find the impedance from B to ground. We're going to find the impedance from C to ground, and we're going to find our Z total. Now, again, we're going to label these points as A, this is B, this is C, and we're going to throw our ground right there. After we get that, we are going to find our current total. Once we have our current total, we're going to find the voltage for R1. We're going to find the voltage for capacitor 1. And then, once we have that, we're going to do our Kirchhoff voltage loop to verify that we have everything correct. And we also need to find the VB to ground. Once we have that, then once we prove that we're good, we'll continue, we'll move on. Then we will solve our IB and we'll solve our IC. Once that's done, we're going to do our Kirchhoff current law check, make sure we're still good there. And once we are, we're going to finish with the voltage across R2, voltage across capacitor 2, voltage across R3, and the voltage across capacitor 3. And that will be all the points that we're going to find. With the power, we're not going to go into that a whole lot here. We're doing that in the lab. But just remember, like when we solve for it, we want our voltages and our currents in RMS, and then we multiply those values together to get our power. All right, let's get started into this. Maybe if my pens are going to work. Okay, so let's start off again. So our capacitive reactance formula, remember, is 1 over 2 pi times our frequency times our capacitance. So our x of C1 is going to be equal to 1 over 2 pi times our frequency, which is 186, multiplied by the capacitance, which is 330 nanofarads. We run that through our calculator, and we get 2593 at an angle of negative 90 degrees. Now we're going to solve for the capacitive reactance for capacitor 2. And again, we're going to have 1 over 2 pi times our frequency, which is 186, multiplied by the capacitance, which is 1.5 micro. The capacitive reactance of capacitor 2 is equal to 570.448 at a negative 90 degrees. Okay. Now that we have that, we're going to solve for the capacitive reactance for capacitor 3. So we have 1 over 2 pi times 186 multiplied by 68 nano. Capacitive reactance 3 is equal to 12,583 ohms at negative 90 degrees. Okay, so now that we have the capacitive reactances found, we have the other half of the equations that we need to solve for our impedances. So I'm going to go ahead and switch colors. So when we do this, our impedance, So the impedance from point A to point B, which is going to be R1 plus X of C1. So we have 430 ohms, or 4,300 ohms, plus J of 0, and our X of C1, as we recall, is 250 or 2593. Excuse me, I need to rewrite this because these are in the rectangular form. 0 minus J of 2593. We add those together. Remember, we add like terms, keeping our imaginary separate. So the final voltage from ZA to B is equal to 4,300 minus J of 2593. And we're going to want to convert that into polar as well. So that is also equal to 5021 at negative 31.091 degrees. So there's our total impedance from point A to point B, which is R1 and C1. The next part we need to find is ZB, which, we come back up here and look, it's going to be from point B to ground. So we go through R2, through C2, and then to our ground. So it's R2 plus X of C2. So ZB is equal to R2, which is 5,600, and J of 0, because it's just the resistor. That's added to our reactance, which is 0 minus J of 570.448. We add those together, and that total comes out to be 5,600 minus J of 570.448. And again, we convert that into polar. So the total value of that will be 5629 at an angle of negative 5.816 degrees. And then ZC is going to be R3 plus our reactance for capacitor 3. And that is equal to 1200 plus J of 0 plus 0 minus J of 12,583. ZC gives us a final value of 1200 minus J 12583. Convert that to polar as well, and we get 12,640 at an angle of negative 84.552 degrees. Okay, so now one thing we kind of want to look at. So back here we have on ZAB, we want to kind of look at the relative closeness to each other. So we have 4,300 and 2593, fairly close, but the resistor is winning. So this is going to be more towards the 0 instead of the negative 90, and it's going to be just on this side of the negative 45. If they were equal, they would be at negative 45. ZB, however, the resistor is much larger, 10 times larger than 570, than the reactance, so we're going to be approaching 0. So in this case, you can see we are getting closer and closer to 0 with the negative 5 degrees. And then in contrast, we look at ZC, we have 1200 ohms in comparison to 12,000 ohms. Again, 10 times difference. So that's going to be the controlling factor, and we end up with a value that puts us right up next to the negative 90 degrees if it was pure capacitance. So we can still see this relationship as we go. Okay, so now that we have our impedances for each of the different branches, so we have it for just the series part and then the two parallel branches, now we need to solve for our Z total. So remember, our Z total is going to be equal to ZAB plus, because we're condensing it with the two parallel branches into a single series circuit, is going to be ZB in parallel with ZC. Now again, we can rename this as one value and call it Z parallel total. So to find Z parallel total, it's going to be using the reciprocal method again, 1 over ZB plus 1 over ZC. Now we're going to go through and solve this just like we did before. We're going to take the reciprocal of both sides to simplify this equation down. So we end up with the admittance of our parallel total is equal to 1 over ZB plus 1 over ZC. Now we're going to take the values that we have from each of those, we're going to plug them into the equations, and we're going to solve for them. So the admittance for the parallel total is going to be 1 over 5690 at negative 5.816 degrees. That's going to be added to the admittance of ZC, which is 12640 at negative 84.552 degrees. Now when we run those through, we get 175.747 micro at a positive 5.816 added to 79.114 micro at 84.552 degrees. So now we look back and see, okay, what function are we wanting to do on this? So again, we look back and we're trying to add these two values together. So to add, we have to convert these two guys into rectangular. And then we'll end up converting it back because we're going to multiply with that value later on. So we end up with ypt is equal to 174.842 micro plus j of 17.809 micro, and that is going to be added to 7.511 micro plus j of 78.757 micro. So there's our two values. So again, we're going to combine common terms, real with real, imaginary with imaginary. So our admittance total is now equal to a total of 182.353 micro plus J of 96.566 micro. Now we are going to be using our total impedance to find our current, and we do that by taking our voltage divided by this total impedance. So we're going to have to convert this guy back into polar when it's all said and done. Plus, we also have to, in one step before that, we have to get our admittance back into impedance, and so we have to take 1 divided by this value. So either way, we're looking at division. This value here has to be converted into polar. So the admittance parallel total, once we do the reciprocal of this, is, not really reciprocal, is once we convert this rectangular value into polar, is going to be 206.343 micro at an angle of 27.904 degrees. Now we take the reciprocal of this value because it's in polar form right where it needs to be. So Z parallel total is equal to 4846 at an angle of negative 27.904 degrees. And there is our impedance total for the parallel branch. Now one other thing to note too is to get our Z total, remember we have to add this value together. So to add, we need to convert this value here into rectangular so we can add it to the rectangular value of our Z total. So to do that, we're going to use our formulas for the R cosine theta, and our Z cosine theta for R, and the the z sine theta for our imaginary value. So this ends up being 4283 minus j of 2268 is what that comes out to be. So now we take our z total is going to be equal to the impedance from A to B plus the impedance of C. And they're both in rectangular because we're adding things together. So our z total is going to be equal to our 8583 minus j of 4861. So that's the impedance of z A to B. We're going to add that to this value that we just found up here. So we got the 4283 minus j of 2268. And again, add like terms. Our impedance total comes out to be 8583 I jumped the gun on that. I apologize. This is our answer. 8583 minus j of 4861 is our answer for this combination. So the impedance I wrote down wrong. And again, I apologize. I'm reading my notes backwards. The impedance that we found earlier for A to B was 4300 minus j of 2593. Now when we add those together, they're going to give us this correct value. Again, I apologize for that error. Hopefully it's doesn't cause you guys too much stress. So now we need to take this, convert it into polar, and with that, this becomes 9864 at an angle, I can write that better, at an angle of negative 29.525 degrees. Now, we're going to take the polar value of this, because we're going to be doing division again, and we're going to solve for our current total. So if we come back up and look real quick at our list of what the things we're trying to find, we have found X of C1, X of C2, X of C3, so the capacitive reactance for all the capacitors, the impedance total from points A to B, which is our series, R1 and C1, the impedance of part B, which is our resistor 2 and capacitor 2, ZC, which is resistor 3 and capacitor 3, and then we found the total impedance of the entire circuit. So now we're on to our I total, and then the voltage drops across R1, C1, and then from VB to ground, and then we'll do our Kirchhoff voltage loop next. So we come back down here. Our I total is going to be equal to the voltage total divided by the impedance total. And that gives us, we started out with 20 volts peak at an angle of 0, divided by this impedance, which is 9864 at negative 29.525. So run that through our calculator. I total comes out to be 2.028 milliamps with a phase angle of 29.525 degrees. Now, continuing on, we're going to take that total current and we're going to find the voltage drops across each of those first resistor and capacitor components, because that is the current going through them. So VR1 is equal to the I total times R1. So now we have 2.028 milliamps at an angle of 29.525 multiplied by R1, which is 4300 at an angle of 0. So voltage drop across R1 is going to be equal to 8.72 at an angle of 29.525 degrees. VR2 sorry, keep jumping these ahead, VC1 is equal to the current total times the capacitive reactance of C1. So VC1 is equal to 2.028 milliamps at an angle of 29.525 multiplied by 2593 at negative 90. Voltage across capacitor 1 is equal to 5.259 volts at an angle of negative 60.475 degrees. And then the remaining part is the voltage dropped across B, which is our parallel branch. So it's going to be the current total multiplied by the impedance of the parallel total. So we have 2.028 milliamps at an angle of 29.525 degrees multiplied by this impedance value, which we had was 4846 at an angle of negative 27.904. So this voltage drop across this whole parallel branch (9.828) at an angle of 1.621 degrees. All right, we got through those parts. Now we need to do our voltage, our Kirchhoff's voltage loop, to double check to make sure that what we're putting in is being dropped across these three components. So our Kirchhoff's voltage loop, if my pen chooses to respond. There we go, finally. So my Kirchhoff voltage loop for this part of the equation is going to be VR1 plus VC1 plus VB minus VS equals 0. Now again, I'm just going to move VS over to the other side to make it easier. So we have VR1 plus VC1 plus VB is equal to VS, which is how we know Kirchhoff's voltage law should go. So we end up with 8.72 at 29.525 degrees added to 5.259 at negative 60.475 degrees added to 9.828 at 1.621 degrees. That whole has to be equal to 20 volts at 0 degrees. Now again, we're adding, so all these guys we have to convert into rectangular. So we end up with a 7.588 plus J of 4.297 is our first term. The next term, that converts to a 2.592 minus J of 4.57 576. Then the last value we have is 9.824 plus J of 0.278, and that's equal to a 20 plus J of 0. Now again, we're going to combine like terms together. So all these added up is equal to 20.004 minus j of 0.001. And for all intents and purposes, that equals our 20.0 plus j of 0. So since those are equal, we good to continue. All right, on the next part, so now that we have those, we know we're good with our voltages. Now let's find our individual currents, individual branch currents. So the current going through branch B is going to be equal to the voltage drop divided by the impedance of that branch. So we end up with a 9.828 volts at an angle of 1.621 degrees divided by the impedance, which is 5629, at an angle of negative 5.816. The current going through branch B is equal to 1.746 milli at an angle of 7.437 degrees. The branch current for branch C is going to be the same voltage because they're in parallel, divided by the impedance of that branch. So we have 9.828 volts at an angle of 1.621 degrees, divided by the impedance, which is 12,640, at an angle of negative 5.816 degrees. That calculates out to be 777.532 microamps at an angle of 86.173 degrees. And that is our value. So now, after we have that, we have those two currents. Sorry about that. And now that we have these two currents, now we can apply Kirchhoff's current law, which states that current going into a node has to equal the current going out of a node. So in this case, our I total has to be equal to the IB plus IC. Only places for current to go. So in here we have our I total is 2.028 milliamps at an angle of 29.525 degrees, and that is equal to 1.746 milliamps at an angle of 7.437 degrees, added to 777.532 microamps at an angle of 86.173 degrees. Now we're adding, so we have to convert all these guys into rectangular so we can get those values. So we end up with a 1.765 milli plus J of 999.405 micro, and that's equal to 1.731 milli plus J of 226 micro. That's added to a 51.896 micro plus J of 775.798 micro. So again, we're going to add like terms together, and we end up with 1.765 milliamps plus J of 999.405 micro. And that is equal to 1.783 milli plus J 1.002 milli. So now as we look at that, these are still relatively close. We're only 13, 18, what do we got? 65 to 83. So yeah, we're 18 millivolts essentially off from this value, so we're good there. That's well within our 5% tolerance. And the 999 micro is just a few notches slower than the 1.02 milli, 1.002 milli. So here, so both are equal for all intents and purposes. So we can continue. And those are our two double checks that we want to do, is our Kirchhoff's current law as well as our Kirchhoff's voltage law. With those two satisfied, we know that we're doing the rest of these right, and we're not wasting a bunch of time. So now that we've verified that those currents are good, now we want to find the last four voltages. So we have the voltage drop across R2, we already found R1, is equal to the current B times R2. So we have 1.746 milliamps at an angle of 7.437 degrees. Multiplied that by the value of R2, which is 5.6 K at an angle of 0. Voltage drop across R2 is going to be equal to 9.778 volts at an angle of 7.437. And then we're going to solve for the voltage across capacitor 2. So it's IB times X of C2. So 1.746 milli at 7.437. And that's going to be multiplied by the 570.448 at negative 90. So the voltage across capacitor 2 is going to be equal to 0.996 volts at an angle of negative 82.563 degrees. So now if you wanted to, you could go through and do a Kirchhoff's voltage loop to verify that voltage of R2 and the voltage of C2 add up to equal VB, which is the voltage across the parallel branch. But honestly, since both our Kirchhoff's voltage laws and our current laws have already been satisfied, I feel fairly confident that we don't have to go through that next step. But you can if you want to. Okay, so that gives us our final capacitor voltage, or final voltage for capacitor 2. Now the last two that we have is we need to solve for VR3 and VC3. So VR3 is going to be the current going through branch C times our resistive value. So we have 777.532 microamps at an angle of 86.173 degrees. That's going to be multiplied by 1.2 K at 0. So the voltage drop across R3, after we run that through our calculator, is 933. Actually, we can go 0.933 at an angle of 86.173 degrees. The voltage across capacitor 3 is the 770 is IC times X of C3. So the 777.532 micro at 86.173 degrees. And that's going to be multiplied by the 12,583 at negative 90. Go away. So the voltage drop, of course, now my pen doesn't work. So voltage of C3 is equal to 9. Oh, come on, I'm almost done. So close, I know my pen won't work. I hate this. There we go. 9.784 volts at an angle of negative 3.827 degrees. And there is our final answer for this circuit. Now we have all the voltages solved, we have all the current solved, and we're good to go. And like I said, we can go through and find the individual powers for these guys. But right now, I don't think we need to. Just come back up here and double check and make sure we have everything. We did solve for our IT, we solved for our VR1, VC1, VB, we did our Kirchhoff voltage loop, we did our IB or IC, the Kirchhoff current loop to solve and double check, and we have our VR2, VC2, VR3, and VC3. So with that, that is the second example that we have for series parallel. And like I said, if you guys do have any questions, please feel free and ask. The test is going to be due on Monday at midnight. That way you guys have a chance to go through the weekend and be able to go through these problems, answer any questions you have, and get through the quizzes. Like I said, please let me know if you do have any questions. You can call me, you can text me, and then also I will be on with the on Zoom between 8 and 11, and I will be on from 1 to 3. So if you do need help, you can always pop in there and get help live as well as reaching me other times. I will be around my house the other times as well, so like I said, feel free to contact me, get a hold of me with whatever you need. If you need help outside of those times, I'm going to be on Zoom. Okay, hopefully you guys are able to understand this, and if you do have any questions, like always, please feel free and let me know.